Can you hear me well? Great. Good morning. It's actually good to wear a hat. All right, welcome to Computational Methods for Structural Design. My name is Jonas Coersmeier. I'm delighted to chair this session. Yesterday I presented in the conference session Advanced Materials, and you can see my work up in the faculty show, beautifully curated by Ferda Kolatan. My work in design computation began at MIT when I was a student of the late Bill Mitchell. It was through Bill that I made my first contribution to ACADIA with a project coming out of his studio. He called it the Studio of the Future. And with it, he tested hybrid forms of remote teaching and learning. And now, just out of the pandemic, or so we hope, it is striking how accurately he had anticipated that what we have become so accustomed to in physical and Zoom space. I'd like to take a moment to welcome the students that are in the audience online. Bill founded ACADIA in 1981 together with other pioneers of design computation. I believe he actually coined that term, and I wanted to take a moment to remember him. And now I'd like to ask all the authors to join us here at the panel. The title of this session, Computational Methods for Structural Design, is composed of three rather flexible terms: computation, structure, and design, in combination with several possible meanings. It may refer, for instance, to the design of structures or the structure of design. And if it refers to the design of structures, are we looking at physical building structures, urban structures, or data structures? It was Cecil Bauman here at Penn who pointed out that structures design is not limited to the redirection of physical forces, but may also elaborate connecting patterns of information of all kinds. The papers in this session address all of the above. At the institutions represented here, University of Pennsylvania, Penn State, University of Stuttgart, and UT Austin, a networked understanding of structural analysis and design has been developed with groundbreaking achievements even before the advent of the digital in architecture. We may, for instance, think of the intricate physical models developed by Robert Le Ricolet as a means of removing mass in structures or to find answers for a simple and brilliant question, where to place the holes. Or we may think of the physical computation models developed by Frei Otto in Stuttgart and the pioneering lightweight structures they informed. Here we see an exchange actually between those. Frei Otto's Special Research Unit 230, studying buckling structures previously worked on by Robert Le Ricolet. A diagram here of Frei Otto's hybrid structures in line with the theme of this conference. And one of my favorite sketches by Frei Otto, expressing his deeply intricate and integrated thinking about structures, a legacy brilliantly carried on by a team of authors here today, Achim Menges and his team at the ICD in Stuttgart. Today, we get an insight into the state-of-the-art in structural design, even beyond early digital topological and parametric models, as the authors involve cutting-edge machine learning and agent-based systems. I'll now introduce the authors and their papers. And then we ask the authors to please present their work. And after each presentation, we do a Q&A. And if the time allows, afterwards, we do a panel discussion. The order of presentation is loosely arranged according to the size of the structures addressed in them, from urban to textile fabrics. However, the papers all address multiple scales. The first paper specifically addresses part-to-whole relations, or part relationships, as the author calls it, between architecture and its city, from prefab building components to urban form and policy. Building Synthetic Data Sets, or How to Learn from Future Architectures, by Daniel Koehler. The author asks, what if one cannot rely on build on existing data when exploring emergent characteristics in building settlements and the city? His paper proposes a workflow to simulate entire data sets. In a case study, it exemplifies how quickly one can generate and analyze a set of buildings at the resolution of BIM modeling, and it suggests that synthetic data sets could become a feature of daily design workflows, and it promotes a new kind of typological thinking. Methods for integrating architectural design intent into the agent-based design of adaptive truss structures, by Matthias Maierhofer and Achim Menges. The second paper, the authors of this second paper write that significant material savings can be achieved by providing load-bearing structures with the ability to actively adapt to forces and deformations. They describe an agent-based design environment previously developed to explore adaptable truss topologies beyond established structural topologies. The scope of their research here is to develop strategies to negotiate design intent with the adaptability objectives of such agent systems or agent-based systems. The paper addresses these challenges through the example of elementary objectives common in early architectural design. The third paper, a web-based interactive structural pattern generation tool with graphic statics and machine learning of dragonfly wings, by Zheng and Masoud Akbarzadeh. Akbarzadeh, I'm sorry to butcher your name. This is chair of our conference. The third paper introduces a web-based structural design tool that implements the workflow of graphic statics and machine learning of the dragonfly wing structures. In previous research, the authors, Zheng and Masoud Akbarzadeh, have developed a workflow to use graphic statics to analyze natural structures and machine learning models to generate the topology and geometry of a dragonfly wing structure. And now, in order to help designers to access their method, they developed a user-friendly web-based tool so we all can profit from their engine. Form finding of architectural knitted tension structures, by Farzaneh, Oghazian, Sam Moradzadeh, and Felecia. The research study of the fourth and final paper here shows the potential of different Grasshopper plugins for simulating and analyzing knitted textile structures. It elaborates the form finding and analysis of such structures using Kangaroo 2, K2 Engineering, and Kiwi 3D. Farzaneh Oghazian is a PhD architecture candidate and researcher at the Stuckman Center for Design Computation at Penn State. Her research focuses on developing computational models to enhance the implementation of knits as materials for architectural application. I'm not going to go through all the bios, but just to say that yesterday, right here, Felecia Davis received the Innovative Research Award for Excellence, and she gave an amazing presentation, I find, of her lab's work, and a wonderful presentation on the topic of, or the emotional dimension of textiles and textile design. So much for the introduction. We're very happy to hear from our distinguished researchers now. Daniel, may I ask you to get us started with the first presentation, Building Synthetic Data Sets or How to Learn from Future Architectures.
Good morning, everyone. I want to talk today about the context, sightlines, and background of my paper that I present today. The paper builds on research on discrete computation and how to achieve that or look into compositional qualities. So over the years, we built a quite circular design workflow where you look into the editing of building parts, the figuration qualities, and vice versa, and you create a feedback by looking or building computational, this kind of superpositions, or call it mereologies, and describe then a building type or a building typology actually as a graph, as a network, as a data set, and looking into the distributive means of its parts, like really like making computing really like a hyperlocal value. So that's actually we commonly describe buildings for common values or for commoning a core facade, a structure consistent of parts. And I can do this also with urban values. And of course, it's important like how you distribute that means. Simple example, it's an open space. Is it a park? Is it a courtyard? Is it a balcony? Like distribution of those parts matters. So in previous works, I'm using then agent-based models mostly, discrete parts to do that, to achieve that. Here in that way, it's like I'm asking a stair, or let's say all generated, so I'm asking stairs to make a building, making a library, like the discrete version of Kohlhaas Chaussee library. I can do this also or using it much more with top-down strategies, with consensus strategies, or using smart contracting as a kind of consensus of those simulations. And over the time, like you always, you have these learning processes, but why you not begin that data which you accumulate on the way in itself to look to qualities of that, and begin to learn actually, gather that data much more structured, and begin really to look into what are this kind of like these communal qualities in the sets. We have definitely a problem with collecting, gathering data in architecture. If we want to gather, derive knowledge from plans and drawings or typical architecture presentations, these are expert drawings. They're very hard to read, but also I think they can't really grasp the full complexity of the built environment. So you can see this vice versa. Also, we can ask now, can you really predict from existing data? Like, is a future kind of living, like really inherent in existing plans? Let's ask this much more categorical. Like, can I really build carbon negative cities from cities which are not? No, that's mapping actually the carbon footprint of Austin. If we would build every city like Austin, it's 3.5 planets of forests which you need for carbon sinking. So it all relates like to the question like, if we train an AI with data, these are Dennis Hasabi's seminal slides on the kind of idea of creativity with AI. You need so much data or such like a supercomputing power and sophisticated algorithms that you make the jump not only from interpolation to extrapolation, but really like to invention. Is that really possible? Or do we combine this actually with synthetic data, with human design intelligence, and complement actually existing data, or like completely exchanging that kind of data? So it's a question of affordance, but also can we actually play a role in computer science, like really with AI models today, or like just remember Midjourney's model, for example, it takes $1 million to train only one iteration of that model. We don't have that resources as architects. So we need kind of ideas of affordance with machine learning. It's an old idea, relying on synthetic data. That's an industrial standard, you could meanwhile say, since 6-7 years. The game engine Unity has also like a nice library, which I begin to implement simply and apply like for architecture and like now generating Vivat buildings by interfacing with simple BIM prefab parts, I simplify them, but like have a simple interface to Grasshopper or Revit to exchange them, simulate that. Also for saving outsourcing or saving those once simulated configurations. So make this really truly bottom up. So I'm interested in really those chunks. So something which doesn't look like a common plan and so on, and begin like really from that to accumulate data. So like really looking to the rawness of, in a way, composition, like gathering all kind of feature data. You can, of course, it's not only combinatorial design, you can also now like implement procedural methods, or like larger parts, or like facades and so on. And basically like the sets I compute then with a more logical approach that begin to mix different sizes of understanding actually what actually is a part, what's a composition. Do I now compose a building out of rooms, of apartments, or of blocks, and so on and so on. No? So this very quickly goes endless. Usually I'm interested in a kind of synthesis or reading this and building this and using this as an architect. So like these sets are in a way like a side product of my common work. So with the sets, like of course they're also content driven. Here's for example one where this is slow paced, that it looks nice simply. Where I'm mapping the standard American household, like the square footage, but just extended with vertical farming, like what that family would need. Here it's paced actually to the pace of planetary building construction. Like you chunk out now 1 second, let's say, or not like further like you. Is also is a great question, like at which size actually you want to build, how you actually disconnect that from a typical understanding of typology. So really making it raw, actually how we understand or relate those kind of plan making. So this just scales up. This is like 1 hour of architecture which we build. This is like 1 day of architecture which we build at planetary scale. Interesting is now I can do this on a laptop. So how much computation do we actually need for architecture? So on the left side, you see now real-time construction pace, planetary. Let's compare that to the standard of up-to-date, like or standard state-of-the-art text or like language models. So Google's Palm model has 500 billion parameters. It's trained on, or has 500 trillion parameters. At the ceiling top of like when we need like 10 billion inhabitants, a ceiling would be 4 billion homes with that. That would mean if we would train a comparable model with architectural data, you could have each single home with 135 unique features designed. With that kind of model or computational kind of the qualities which we have. So it means the idea of like what we make as being particular, like you see like how computation actually should change our whole mindset on what we research. A side note, a sideline, with computation. Or here, like a high-rise, 400,000, 500,000. Thumb is like, you could say per household I have 1,000 building parts in a way in a BIM model. So it relates to 1.5 unique parameters in such a model for crazy. So I assume, or I predict, or what I write in the paper, that we, with more computation, of course, integrate more kind of features which don't rely at all to the building, like environmental features and so on. So by side, I'm also generating or now like synthetic features, or looking here, like for example, of course you cannot read this, but like over sun insolation, measuring, looking into carbon footprints of that building and so on. So challenging part of generating such data is of course that you have a unified distribution of your values. That means also that before like that a machine learning with patterning is actually not really realistic because it doesn't include patterning because unified distribute, you should at first filter that. But it means also the advantage of that is why not look after doing a set, doing a subset which is in a way like filtered and compressed to certain features. When we use that, or when I use it in design studios, so it's now real-time kind of generation of sets, so you can do it also much more intuitively. You make this inside the design realm that you just, over yes or no of, no, I like it, I don't like it, much more intuitively gather that data, no, which is nicely already segmentically structured, ordered, and which you can, for example, use now training a gun for a distribution of voids, no, and then you make a nice quick project on traditional. Okay, shortcomings of that. Of course, like with kind of like bottom-up assemblies, the kind of latent space is quite narrow. And also, as I said already, like the kind of like it has a high entropy over that. So learning patterns is rather difficult with that data. But also like for what we want actually to learn, what we want actually to optimize. So I'm quite happy when I'm opening actually a data set or a BIM model, a text file, that it reminds me that. And it's much more like when I'm looking into kind of the idea of what do I optimize, what do I look for in a sect, then there's of course this history in urban or at urban scales that we look actually into this kind of like openness of data, or seeing actually at first that what I design is also a contribution of that what's possible is a politics in itself, and how to as a contributor to that. If I would write this paper today, not in April, it would be much more colorful. So I'm doing the same now, place that actually with a different machine. Also like a quick outlook onto what could be actually this kind of contextual data integrating into the set. So it's, for example, like chunking through a set now. What if like embedding economic data? This is now like refers to family business, a cooperative business, or I'm working with stacks in a city. But overall, like what I have the conclusion with working with sets is more like a different mindset, so how I see buildings, which is actually in itself as a synthetic environments, or like rhyming on Joseph Beuys' like social sculpture quote, like architecture is like spaces and data, using language, thoughts, action, and objects. Thank you.
Excellent. Thank you, Daniel. Are there any questions in the audience for Daniel? I have so many questions. This is an amazing presentation, and it sparks so many ideas that I would love to debate. However, I think these immediate questions after the presentation are supposed to be of technical nature. Is there anybody who has a technical question for Daniel? No question for you right now. Okay. So then, Matthias, maybe you want to jump in? Thank you.
All right, that's me. Hello, everyone. I will now present the paper Methods for Integrating Architectural Design Intent into the Agent-Based Design of Adaptive Truss Structures. My name is Matthias Maierhofer. I am a doctoral researcher at the ICD in Stuttgart and the Collaborative Research Center 1244, focused on adaptive structures and envelopes. In the context of this presentation, adaptivity refers to the concept of ultra-lightweight construction, through which, compared to conventional construction, CO2 equivalent emissions can be reduced by up to 50%, while at the same time doubling service life. This is achieved through a shift in the conception of load-bearing structures from systems that merely withstand loads to ones that actively adapt to them. To illustrate this a bit more tangibly, we could take a look at wind loads, which occur at different intensities and frequencies, whereas lower wind loads are typically more frequent than higher ones. In practice, however, high and infrequent loads are typically those that govern structural design, resulting in structures that are underutilized for most of their service life. In view of a higher material utilization, ultra-lightweight construction proposes to design for smaller loads as such are more frequent. And to ensure safety and serviceability in infrequent events of higher loads, strategically integrated sensors and actuators are activated to address resulting stresses and deformations. In other words, we could also say what these actuators and sensors do is to actively induce counter forces and deformations to eliminate those caused by the load case. The first ever realized ultra-lightweight structure is the Stuttgart Smart Shell, spanning 10 meters with a thickness of 4 centimeters. This hydraulically anchored timber shell is capable of detecting unfavorable deformations, which are autonomously compensated through a distinct change of its adaptive boundary condition. Within the Collaborative Research Center, our goal is to transfer this principle to an architectural scale and application. This endeavor is accompanied by the development and operation of an adaptive high-rise structure conceived as a spatial truss consisting of 128 elements, 24 of which are actuated. The downside here, though, is that the system is based on a highly conventional structural typology, not capable of fully exhausting the potentials provided by ultra-lightweight construction due to its limited adaptability. Here, adaptability describes the degree to which a certain topological layout allows for forces and deformations to be manipulated. And the means for measuring adaptability, in turn, are so-called redundancy matrices, which contain millions of entries for structures of a significant scale. So rather than merely equipping conventional structures with sensors and actuators, the real challenge and our aim is to develop design strategies to leverage this information to both ensure genuine adaptability and to explore the architectural opportunities that are inherent to the departure from rigid and repetitive structural typologies. For the purpose of this problem, we identified agent-based modeling, short ABM, as a particularly suitable design method. ABM is used in many fields for gaining insights into the dynamics of complex systems. This in turn means exploring the relationship between system behaviors on the micro level and the respective emergent phenomenon on the macro level. In our case, we intend to gain insights into how local topological conditions affect the global adaptability of adaptive structures. And ABM is also particularly relevant for architectural design due to its ability to integrate and negotiate a variety of potentially conflicting design objectives. Also, compared to black box optimization algorithms, agent-based models are inherently interactive, as their immediate response to interaction provides instant design feedback. The methodological challenge inherent to defining an agent model is the definition of what its constructs represent, as well as the abstraction of global design objectives to low-level agent behaviors. Our agent model is defined as follows. We define agents to represent truss nodes, whereas a truss element is represented by an explicit agent pair. Truss fields are represented by an implicit group of 3 or 4 agents, and an explicit pair of agents within or across truss fields define truss bracings. Agents are embedded into 2 types of environments: a topological environment that represents the truss structure, stores truss-related information, and defines the topological neighborhood of agents. And a Euclidean environment that, on a global level, represents the building site, and on a local level, the floor slabs agents are constrained to. Accordingly, agents exhibit 2 types of behaviors: position-oriented behaviors, which result in translation vectors and determine truss geometry, whereas truss topology is determined by topology-oriented behaviors, through which agents vote for elements to be added or removed. What we have focused in the first step was translating adaptability objectives to a series of bespoke topology behaviors. In a nutshell, at every iteration, the agent system evaluates the current truss topology, and based on this information, agents' votes for elements to be added or removed to the system. This video will show one such exploration cycle, starting with a structurally determinate base topology with 72 out of 150 possible elements. And although our behaviors that we have deployed here are fairly simplistic, they led to topologies that perform just as well as our hypothetical benchmark topology with all 150 elements. Maybe this is a moment to quickly drink a bit of water. But since we are aiming to introduce structural adaptation to the architectural domain, design methods cannot focus on adaptability, but must also acknowledge architectural objectives. Consequently, we also need strategies for translating design intent into constraints and instructions in order for them to be negotiated with adaptability objectives. The work presented in this paper makes the first step in this direction by identifying and outlining integration strategies specific to few objectives common in early architectural design. And also in the interest of time, I will now just introduce them on a very sort of like superficial level. First, considering that architectural design briefs typically specify basic programmatic requirements, designers must be able to translate such into a preliminary truss topology with a resolution that is adequate for the respective design task. The proposed approach involves the definition of programmatic zones from which potential truss nodes are extracted and a preliminary structural layout that fulfills basic truss design parameters is derived. Our approach to informing agents about massing or site-related objectives is to encode information in the Euclidean agent environment. To do so, designers define areas within the three-dimensional instance of the environment that are to be avoided or populated by agents. In a second step, this information is mapped to the corresponding two-dimensional instance of the environment and translated to vector field that attracts and repulses agents. On a more local level, a challenge is to architecturally account for the fact that here topological conditions unfold in unintuitive ways. In other words, if not constrained, truss members might occur in areas where they interfere with architectural spaces. To allow designers to proactively address this, an approach based on the concept of zones, as shown before, is proposed. For example, a circulation-specific zone applied to all circulation areas where fields in the force labs are defined to remain free from bracings to install elevators or staircases, for example. Such zones can also serve as a means to encode geometrical information. Three corresponding geometry-oriented behaviors are defined: an area behavior to maintain desired target areas assigned to a field, an angle behavior to maintain a desired angle between two adjacent truss members, and a length behavior to maintain desired truss member lengths. The last aspect I would like to touch upon is design feedback for designer interaction, to inform designers about the implications of their interventions, or for the case of conflicting design goals that cannot be mediated on the agent level. Developing means for agents to communicate the origin or even potential solutions for conflicts would thus allow for a more productive and genuine collaboration between human and agent designers. To summarize, this work lays the groundwork for designing architecturally meaningful adaptive structures. Specifically, it provides a methodology that is receptive to both architectural and adaptability-specific design requirements, and thus a sound methodological foundation for the next step of implementation and validation. With this, we aim to ultimately ensure the designability of adaptive architectural structures and consequently to facilitate the dissemination of structural adaptation as a relevant technology for low-emission construction. Lastly, I would like to acknowledge the generous funding from the German Research Foundation. I would like to thank my collaborators from Structural Mechanics, as well as my colleagues from ICD with whom I've co-developed ABXM, our recently launched agent-based modeling framework. Thank you.
Thank you very much, Matthias. Are there any questions for him? Yeah, over there, please.
Yeah, can you elaborate a little bit on the tools you
Is this on? Yeah. Am I understood? So, I mean, on a general level, this is really just like Rhino, Grasshopper, and custom code. And also, that's why I also mentioned in the end, we developed our own agent-based modeling framework. We had the issue that everyone always started setting up their own agent system in like different ways. It was really impossible to have a common infrastructure. So we can like always skip this first step of setting up a system and just jump straight to building your own application. So that's really sort of like the main, the core of my sort of like methodological developments. It's available on Food for Rhino. ABXM. If you Google ABXM something, it's gonna Food for Rhino. I mean, the concept is, so what we provide is the ABXM core, which are sort of core functionalities like all the constructs, pretty much a template. And then this would be an add-on to this core, which is then it's sort of like standalone application, more or less. In my case, the feedback is based on these redundancy matrices. So they're recomputed sort of like in a parallel fashion and then distributed to the agents at each iteration.
Thanks for the talk. It was very interesting. I'm wondering about the actuated elements. How do you decide which races get actuated? And also, is there any consideration? Okay, I'll say it again. How do you decide which braces are actuated in the actual structure? And also, is there any consideration for like construction sequencing, like stability during construction, or is this just sort of a final analysis that you do on the finished structure?
So the construction sequence, I mean, could be for sure more sophisticated than it is for like nowadays truss structures, but it actually doesn't really matter so much because the structure within itself is already like stable. Like the only thing that really these actuators do is to make sure that like certain deflection limits are maintained, or like stresses over a long time don't exceed certain thresholds, so you can like set it up even if like there's an outage, like it's fine. And the placement of actuators is also very closely related to this. So basically the redundancy matrices also give us information of where to put actuators in the system. But our goal is, and so this is the concept of overall adaptability, there's just like topological conditions that are more sort of like receptive to actuators doing something than others. So that's why we focus on this, because the actuator placement would kind of be a secondary step of then just like also deciding if you want like more local or global behaviors in the system, so that, but it's not so design relevant actually. Thank you.
Yes, please, up there.
Does your design involve also morphological, like morphing of the structure, or just static, and the actuator just responding on the, like you say, like certain deflection, like, or you allow some movement in the structure?
So basically, what the actuators do is really like probably like a centimeter is the largest. So it's really like minimal actuation. Like you can barely see it happening, which is kind of a bit the funky thing, because it's the opposite of what we usually conceive of as adaptive structures, right? You see something moving, but we do the exact opposite. We try to take movement away. So if you don't see anything, it kind of worked.
Great.
Are there any more questions? Maybe I can follow up on the last two questions, actually. It's a fascinating study and system that you're developing. And you start out with the promise that we can actually save material, and that's so important. The body of the study was mostly from the perspective of the designer, I would say. And I was wondering if it needs to remain ultimately that the topology designed is the one the structure receives, or if the actualization can actually be at the level of what your agent-based system is establishing, which is the topology, the connection between the members in that structure. So it's kind of implied in the first question, I think, that there is a given topology and relationship of these members coming out of the designer-oriented system, and then the structure is reinformed by some of those informations for minute changes within that system. Can you imagine a future where we have these systems designed from the perspective of the structure itself, that the structure could potentially reassemble itself?
Actually, so basically, my research, as it's sort of like outlined, involves two steps. The one is kind of in this direction, and the second step is exactly that. So because on the one hand, we're designing the structures that have maybe double service life. They are 100 years, but have the most deterministic sort of like structural layout ever that is probably not going to satisfy all our requirements up until like in 100 years time from now. So the question is, how can we translate or sort of like augment sort of like this digital agent system with the then deployed physical system? On the one hand, to sort of like even just understand, can I take this diagonal out, or like would this cause like a major impact on the entire system, or like where would I have to change something? And the other question is also like, how can we learn from what the structure went through, so that ultimately the adaptive structure itself could propose interventions that affect the structural architectural space in some way.
Great. Maybe we can continue this later in the panel discussion as well and move on to our third presenter, Zheng, a web-based interactive structural pattern generation tool with graphic statics and machine learning of Dragonfly wings.
Okay, so hello everyone. My name is Zheng. I just graduated from a PhD program here at Penn. I'm happy here to present our recent research from Procedural Structures Laboratory about a web tool to generate structural solutions based on graphic statics machine learning. So let me first play this introduction video of our previous research of the methodology.
Nature has always been the source of inspiration for designers, engineers, and scientists. Among a variety of natural structures, a dragonfly wing is an instance of a high-performance, lightweight structure that has intrigued many researchers to investigate its geometry and its performance to be used in bio-inspired design. The projected 2D pattern of a dragonfly wing can be regarded as a structural form in which most of the cells are convex polygons. The convexity of this network reassembles the geometry of a tension-only or compression-only network. We can use geometry-based equilibrium methods known as graphic statics to analyze the equilibrium of such networks. For instance, a closed convex polygon of forces can be constructed around each node of the network, which represents the equilibrium of the node. These polygons together construct what is called the force diagram in graphic statics. The length of each edge of the polygon represents the magnitude of the force in each member of the structure. The convex network of the dragonfly wing can be analyzed using graphic statics in an iterative process. First, an initial graph of the force diagram is constructed, and then the edges of the graph are iteratively become perpendicular to the edges of the structural geometry. Besides, the Minkowski sum is another representation of the form-to-force transformation, which shows the intermediate status between the form and the force diagrams. According to graphic statics, in the form diagram, the cross-section of the members can be sized proportionally to the edge length of the force diagram, thus resulting in a constant stress structure. Based on the generated form with structural thickness, we compare the similarity of the real and the generated internal wings. For each structural member, we measure the radius, compute the relative accuracy, and average all accuracy values. We further compare 6 wings. The overall accuracy is 91.9%, which proves that the internal wing structure basically follows the rules of graphic statics on the form and force diagrams. Next, we measure the thickness of the external edges in the structural form of the wing, and map the pixel counts to the lengths of the corresponding edges in the force diagram. With the external and the internal force diagrams, the entire force diagram can be obtained. By transforming the entire force diagram back to the structural form, the structural thickness of the entire wing can be inferred. Thus, the predicted dragonfly wing is complete with both internal and external members. Comparing the real dragonfly wing with our generated dragonfly wing, it shows a high accuracy of match. Therefore, graphic statics can be used to reconstruct the network of a dragonfly wing. The force diagram is an additional attribute of the dragonfly wing that includes structural and equilibrium information. These initial results lay the foundation for the second phase of this research, which is related to the generative aspect of the work, with no information about the initial topology of the network. In the machine learning step, our final goal is to generate the entire structural form of the wing from a user input boundary with an intermediate product of the topological force diagram. We firstly precede the form and force data into features, such as the boundary and the main path. These feature images and vectors become the training dataset for the machine learning models. Next, we train 3 models to generate the force boundary from the form boundary, to generate the force main path from the force boundary, and to predict the form length from the force diagram. Finally, the user can input the boundary of a new form, and the 3 trained machine learning models with the graphic statics method work together to generate the structural form inside the input boundary. The generated form contains similar features of the Dragonfly wings from the dataset. The training log of the 3 machine learning models also show a fitting and convergence of the training datasets. The generated images become clear, and the loss values for the predict vectors become small. To test the performance, we prepared a testing dataset with 3 categories. As a result, we can visually see the real and the generated Dragonfly wings are highly similar. To further compare the similarity of the wing pairs, we implement an evaluation method based on the area and the circularity of each cell in the wing pattern. It proves that our method can generate structural forms close to the Dragonfly wings from the boundaries. We have also collected the training and testing data for other species to verify the generality of our method. The conclusion can be reached that it can be widely applied to generate structures by learning from other natural species. Therefore, using the trained models, we can input the human-defined boundary of an airplane wing and ask the machine learning models to generate the structural form within the boundary. By inputting different wing boundaries, various wing structures can be generated and applied to the design of an airplane. We then extract the boundary of a real airplane wing and generate our structures to compare their structural performance. In the out-of-plane loading, our structure has higher stiffness and max force, and the failure line influences less to the main structure. In the wind tunnel test, our structure deforms less than the existing structure, which proves that our generated structure performs better in certain scenarios. Finally, based on our graphic statics and machine learning workflow, we implemented a web tool that helps designers generate funicular cantilever structures by user input boundaries. Users can visit the web page and generate structures without any installation on the local computer. In conclusion, our method applies graphic statics and machine learning of Dragonfly wings and generates an entire wing structure from the user input boundary. This method can also be used to design airplane wings or other similar cantilever structures as lightweight and efficient structures for industrial or architectural purposes. Thank you for your listening.
So therefore, it's not finished, sorry. They are just so our previous research about the methodology. So as you know, based on the previous research, so we developed an online design tool that concludes the previous experiment, provide the designers with an easy implemented, applicable tool for generating structural design solutions. So that is the main contribution of our paper submitted to ACADIA. So the contribution of this of our previous experiment is raised to a level combining both academic and practical aspects. So let me play another video of introduction of our web tool here.
Here, we introduce a web-based tool that implemented the workflow in our previous research of machine learning and graphic statics to generate a wing or cantilever structure. First, the web page should receive the input boundary and parameters. The user can select the number of vertexes and adjust the positions of each vertex by dragging them on the canvas. The parameters can be adjusted by changing the values in the sliders. After the adjustment, the user can click the Submit button to send the request to our server and leave an email address to receive the results, usually in 5 minutes. When the server completes the generation process, it will send a CSV file to the email address, which contains the geometric information of the generated structure. The user can download the data file from the attachment and then upload it to the web page to navigate the generated structure and play with the analytical results. In the output control panel, the display of external forces and color coding can be turned on or off. In the case of the Minkowski sum mode, the web page reads the user input of the Minkowski sum indicator and calculates the corresponding status in the form to force transformation. For the instant FEM analysis, we provide 2 types of loading. The first is the self-weight loading for all vertexes, and the other is the point loading for the furthest vertex to the anchor. When the user changes the material setting or structural thickness, a recomputation request can be sent to the server, and the FEM results will be updated in approximately 10 seconds. The color-coded scale is also shown on the right side of the web page when the corresponding FEM result is shown. The scale includes the minimum and maximum values of the percentage of deformation compared to the span, as well as the real values of the deformation in millimeters. Finally, the user can freely decide to fold or unfold each panel to better balance the UI and model display. Besides, restoring these results only requires the local computer from the user. So it does not require a connection to the server to display the results. This makes serving multiple users at the same time possible. Therefore, we have developed a web-based structural design tool that implemented the workflow of graphic statics and machine learning of the Dragonfly wing structures. It helps designers generate funicular cantilever structures without any installation on the local computer. You are welcome to visit our website. And thank you for your listening.
Okay, still not finished. Okay, so in the following slide, so I will show more cases generated by our web tool. So in the first case, you can see that we input different structures with different input boundaries. So the user can select the number of control points in the input boundary and drag the points to adjust their positions. So continuous structure can be generated within the input boundary, which contains the features of the Dragonfly wing. Also, the second case shows one example of controlling other input parameters, such as the subdivision density. So in our previous research, we found that simplifying the structure to a certain degree will improve the structural performance, make it easier to fabricate in the real world. So the user can consider the fabrication ability and adjust the subdivision density. Also, this figure shows the case of Minkowski sign in different stages with different values of the indicator. So the indicator defines the position in percentage of the current Minkowski sign in a form to false transformation. So the user can also view the Minkowski sign in the web tool as an interactive scene. Also, this figure shows the FEM results under different loading scenarios and materials. So when keeping the deformation multiplier constant, the user can also directly compare the FEM results from different structures with different materials as sequence settings. The final case shows the application of our web tool in exporting the result to other platforms for various purposes. So the exported STL model can be imported to a variety of platforms, including modeling software for further adjustment, 3D printing software for digital fabrication. So our web tool completes the loop of logic by accepting the user input and exporting the generated result back to the user. That's it. Thank you.
Thank you very much. Thank you very much. Are there any questions for Hao? No questions? Oh, yeah. Go ahead, please.
Thank you. Great talk. I'm wondering if you're training your machine learning model based on a certain set of applied load cases, how can you be sure that you're not generalizing your results? So if you were to apply some unseen load case, can you be sure that it's going to take it into account correctly, or kind of how do you deal with that challenge?
Yeah, so our assumption of this research is that we assume that the user will input a boundary to generate the structure, and then the structure should perform similarly comparing to the Dragonfly wings. So that's why we connect the Dragonfly wings as the data. Then we try to generate the airplane wing based on this data. But for example, if we use other data set, for example, the water lily flower, that might be corresponding to other types of structure that is similar to the flowers. Yeah. So that's why in this implementation of the web tool, we only use the model which was trained by the Dragonfly wings data, which can only be used to generate the cantilever structure or wing structure which is similar to the Dragonfly wings.
Got it. Thank you.
Yes, please go ahead.
Hi, I had a couple of things. The first thing was, do you have any models which represent the actual process by which Dragonfly wings get created using like a reaction diffusion kind of model, as opposed to modeling your separate system, that you can simulate the real way in which the development of the Dragonfly wing happens?
Well, so we assume, the reason why we use machine is that we only care about the input and output. So we don't know, or we don't care what's between the input and output. So we use machine learning to learn, to generate the output from the input. So actually that's a key point, that we actually don't know how a real Dragonfly wing is grows or is formed. So we use machine learning to simulate or to learn this process of the growing of the, not growing of the direct generation of the wing. So the biggest assumption is that we still don't know how Dragonfly wing performs in the real world and why it's there like this pattern. But we can use machine learning to learn from the results that we can try to simulate the nature based on the machine learning results. Yeah.
The second thing was, what would you say that the best manufacturing method is in terms of, I was thinking for 3D printing, there's some element of directionality and material properties, and you probably want that directionality to be kind of along the structural members. So how would you imagine manufacturing these?
Well, if for the fabrication, if it's just for the case, for example, the case we work for the loading test, we just simply print it with the same material, with PLA, then we can use it to make some like loading test. But for the real wing, I think it's just a very basic design. Then we have to design the joint, and then we should also match the material property of the real material in the airplane wing. Then we can fabricate the real wings.
Thank you.
Hi, thank you. It seems like the user-generated like polyline contour as input could potentially be like limiting to other solutions, and I'm wondering if you're evaluating like higher level input, just like amount of lift, and having it generate that.
Do you mean the input to control the machine results?
Yeah.
Yeah, actually, there was a slide that's showing the complex workflow, which involves like multiple machine models. So in this workflow, we use image-based machine model. So the only input is the boundary image. Then in the web tool, we actually adjust the result by some geometric control parameter, for example, the subdivision density. So after we generate the primary result from the machine learning, we can use geometric algorithm to adjust the network, for example, the density, for example, the sequence. Then we can give more freedom to the user to freely control the results in the aspect of the web tool.
Thank you.
There's one more question.
Just curiosity, technical question. Your static graphics 2D or 3D, and how does it translate to the case that you have a horizontal load? I mean, just technical question on that.
Yeah, actually, for the real Dragonfly wing, it's slightly banded as a very slight 3D curvature. But for this research, we just regard it as the 2D pattern, because in most of the case, we can regard it as a 2D pattern. Then, so still back to the biggest assumption in the beginning, that we don't know why Dragonfly wing is formed in this case. So we use machine learning to learn for that. Then even if it's a 3D, but we can simplify that as a 2D case, because it's almost flat. Then by the loading test, in the end, we can say that our design might contain the feature of the Dragonfly wing. It performs better than the traditional structure. Then our purpose of transforming the feature, the advantages of the Dragonfly wing into the airplane wing, is achieved based on our final experiment. So actually, some reviewers also posted this question, that we still don't have a very real model or real simulation model for the real wing. So that's the mystery of the machine learning. Even if we don't know the reason, but we can still use machine learning to learn the mapping between the output and input. Then we can apply that to some industrial purposes.
Let me ask you a question as well. I know that Masoud's amazing method for calculating polygonal forces is also beautifully deployed in three-dimensional truss structures and not just in 2 dimensions, following the last question. Do you think you can develop us a web tool for that one as well?
Well, it's very similar. So for our web tool, we just use a local server in our lab. Then it actually computes everything. Then the user just to send the request and get a result back. So as long as it can be achieved from, for example, Rhino or Grasshopper, then it can be implemented as a local server. Then we can use this web tool to get input and generate results.
Great, really looking forward to it. Thank you for your presentation.
Yeah, thank you.
Okay, last but not least, we have form finding of architectural knitted tension structures by Farzaneh Oghazian with Sam Moradzadeh and Felecia Davis.
Hello, everyone. The title of my presentation is an investigation on form finding and analysis of needed tension structures in architecture. I'm a PhD candidate in architecture, and I co-authored this paper with Sam Moradzadeh and Felecia Davis, all of us from Penn State University. Tensile, and specifically textile structures, are one of the main categories in building construction. For many years, lightweight structures made with technical woven systems have been one of the dominant methods of developing such designs. Within the last decade, however, other techniques of textile development, such as knitting, have found their way into architecture. Recent improvements in CNC knitting and computational design have increased the viability of knitted textiles in architecture and enhanced the research in this field of study. And here you can see some of the work by pioneers in this field. But why knitted textiles? Knitted textiles have a multi-directional behavior that allows for development of complex shapes, and also it is possible to knit some forms seamlessly, which removes many processes of patterning, cutting, and sewing pieces together. While many research in the knitting focuses on developing methods for CNC knitting, I'm also interested in physical model making methodologies and digital simulation processes across the scales for developing models that are knittable by industrial knitting machine, as well as simple knitting machines, and even pegboards and looms by architecture students. So when we are dealing with the multi-directional material, one of the challenges is simulation and analysis processes and how these digital simulation can help during the design process to architecture students. In this paper, we looked at some common form finding methods for tensile structures, such as transition stiffness, force density, and dynamic relaxation. We didn't go through the details of using these methods, but the fact is iterative computation for producing shapes in a static equilibrium is the primary goal of all of these approaches. We did also a research on available commercial tools for simulating shape and performance on tensile structure systems, and looked at free tools available through Grasshopper and Rhino. And in these tools, we were specifically interested in type of the initial shape should someone input into for the form finding, and if these tools support the structure analysis. For example, in working with Rhino membrane and K2 engineering, the initial shape is a mesh, and in order to get a proper result, the anchor points should be extracted from the initial mesh and should also meet the final position of the anchors. And it is the same for KV3D, but the only difference is that here the input is a polysurface, and segmentation can be done through manipulation of control points. Kangaroo 2 is one of the most flexible in this regard, however. Literature also shows development of methods for simulating the behavior of the knitted textiles. Here you can see some of these studies. For example, Jean Alquist has developed Springform tool in processing, and many other projects use Kangaroo 2, and here you can see some of those studies. To better understand the form-finding process and analysis of the needed textile, the first step is to understand the logics in the needed structure. A needed textile can be made by moving a continuous yarn through loops or stitches that are made previously. Depending on how you pull the yarn through loops, or if you skip needles, combine stitches, etc., you can create different neat structures or patterns. While textile designers are mostly interested in simulation of the behavior of the textiles with different neat structures at the micro scale, architects often use simplifications. Triangle, quad, and hexagon are some of the common shapes used in the literature. And also research shows that surface discretization and mesh distribution affect the form-finding process and the final equilibrium form. It is important what shape will be used as an input of the form-finding process, and specifically for the needed textile. To elaborate a little bit more on this, I'd like to walk you through a process in a digital simulation of the needed textile for a desired form. One can design a rough initial shape considering the effect of the kneading machine settings, yarn type, and knit structure. In the second step, stitch distribution based on the kneading process and stitch sizes define the overall size of the initial mesh. Then comes the form-finding process, which requires defining the boundary conditions, forces, and textile elasticity properties. After form-finding process, one can run structural analysis to study the behavior of the needed textile. And based on these results, go back to the initial shape and manipulate it. After finalizing the initial shape, the kneading diagrams will be generated and will be sent to the kneading machine to be kneaded. Before finalizing the initial shape, at two stages, initial shape can be manipulated, actually. One is during the form-finding process, and the second is after loading and getting feedback from the structural analysis. So one can always go back to the stitch level and manipulate properties of the material and run the form-finding again. For this step of structural analysis, we looked at how tools such as K2 Engineering can give us feedback during the design process. K2 Engineering for Kangaroo is a plugin developed by Cecily Brandt Olsen that contains a set of customized Kangaroo to Grasshopper components that can be used for calibrating goals regarding the structural performance of the tension fabric structures. We also implemented Kiwi 3D from the initial stages of form finding and analysis step. Although form finding with exact mesh distributions might be challenging in Kiwi 3D, this tool could be quite handy for structural analysis. The form found model as an output of the Kangaroo tool can be used as an input for the structural analysis in Kiwi 3D. So here you can see some of the rough results of the simple shapes, stresses in simple shapes like hyperforms, and associated meshes in the initial shape that represent stitches. In this way, we could always call back particular mesh faces and change the property of that stitch and go and get the behavior that we want at the end. To have a reliable model, the digital simulations should always be compared against the physical models. Since the dimensions and shape of the initial mesh are according to the actual needed sample, if we could predict the length change of the meshes at different sections of the model, then we can get a form-found model that represents the actual material behavior. Also, the simulations in this study are done for a series of models of the same shape, but at different scales to understand the behavior change across the scales. As we scale up, the number of stitches in the actual physical model increases, as does the number of stitches, mesh faces in the digital model. This increases the computational process time, and one solution would be to pack a series of the mesh faces into one mesh face. How reliable the model would be is the topic of another ongoing research. So with this, the main contribution of this study is a process of form finding and analysis of needed tension structures using Kangaroo to K2 Engineering and Kiwi 3D, emphasizing on the material behavior and shape of the needed model. The main takeaway of this study is that these tools suggest a new way of practicing that incorporates software that allows for multiple behaviors from a material, a craft, rather than a design being imposed on an abstract material. With the drafted algorithms using the aforementioned plugins, we now have a way to be in conversation with the formation, thus form finding through the material, not form finding onto the material. Thank you.
Thank you, Farzaneh. Are there any questions for her? Yes, please.
Hi, nice presentation. I have a particular technical questions about the slide where you show the input of young modulus, and the difference you show in the values is from 1 megapascal to 10,000 Pascal. So I would like if you can comment your observation through changing the stiffness value of the meshes, because in the picture, it's like not a big difference you can notice. What's your experience in like changing through these values? Because I also work with K2 engineering and trying to find this magic stiffness value for the knitted fabrics, but I don't have an answer, for example. So I wonder if you actually discovered some reference, like how to reference the physical and the stiffness value for knitted fabrics. Looking forward to hear your comment.
Yeah, thank you, Yulaila, for your question. That's a really good question. I think in my cases, I run I do the measurement to get the e-modulus of the textiles of different patterns, and then I will try to input it into the K2 engineering. But I still consider each mesh or each stitch has like 4 edges and input those values there. I'm still working on that. I'm not sure if that's a right one, and I like to get some feedbacks from the people who are working on this and criticize me if I'm doing this wrong. But in the slide that I showed, I wanted to mainly emphasize on the potential of the K2 engineering, that if you use the proper initial mesh with the accurate distribution of the stitches, then you can use this tool, input the e-modulus or stiffness of this of the textile into it, and get some feedback regarding which parts are more under tension, which parts are kinda facing the compression, and then call back those particular stitches, change those, maybe add more yarn to it, or maybe make those more stiffer by kneading them tighter, and all that. And in this way, you kind of have this potential to manipulate the behavior of the textile. I'm not sure if I answered your question or not.
It's more in the break because I'm actually in a very similar moment discovering it, so let's discuss.
Yeah, for sure.
What I hear from you is that the reliability is really dependent on the resolution. So if you're one-to-one, then it's kind of closer, right?
Exactly.
Thank you, Farzaneh.
Yeah, sure.
I think we're slowly migrating into the panel discussion. Are there any general questions to any of the authors? Yeah, James over there.
Yeah, I had one more about the knitting actually. So what the knitting was doing with the patterning and everything reminded me a lot about like curved crease folding, where you're adding additional structure with basically the pattern and adding intelligence to the material and letting the material really speak for itself. Which I found like really amazing to see. But did you? I know it's not the line of research that you're doing, but like adding an additional sort of like scaffolding material to allow you to further express the form finding that you might be doing, like kind of like working in tandem a little bit more with an additional material, or were you just more focused on expressing what your knitting and patterning would be able to do?
Yeah, thank you for your question. So in the form finding process, I already published another paper for the calibrating for the form finding simulation. And in that one, I kind of categorized the mesh lines in different sections of the form, because it kind of works differently. So when you first run the simulation, it assumes that all the meshes behave the same, the length factor changes the same, but actually it's not. So in that one, I was emphasizing subdividing the lines in different sections, and then I was using the optimization tool to kind of automatically find what happens for those lines in different sections. But in those one and in the ones that I presented here, I use just one pattern, one neat structure to make it simplify. But if you have a textile with different patterns or having like different stitch densities in different sections of it, you can also do the same. You can like subdivide those parts and find what happens to the length factor of those particular parts. So in this way, you can have a gradient pattern structure and automatically find the behavior of it over the in the form-found model. I don't know if I answered your question, but
that was great. Thank you.
Sure.
Yeah, it's fascinating. It's really amazing to see and to hear how the work at your institute is, on the one side, very precise and technical, as we just heard, and as we heard yesterday from Felecia, that it incorporates all other dimensions of design, including the emotional one and how textiles inform our emotional relationships to the material. I had perhaps one more question for you, since we referred to Frei Otto earlier and his physical computational models when we are introducing Matthias and Achim from Stuttgart. So it's really interesting to see that you are testing the various scripts for simulation against their physical counterparts. And it did remind me a little bit of the work that Frei Otto did when he was taking measurements and exactly using those measurements for the build structure. This was at a time when we were just transitioning into the digital era, so I think the tools were just available. At the time, the argument was that the physical models would actually be more precise. And I've heard similar things from you and your colleagues in the computational textile field. For instance, that crochet models, topological hyperbolic crocheting, for instance, is still to some degree more, I want to say, precise in predicting a form than the computational ones. And I guess my question ultimately is, are we at a moment where we're transitioning from simulating something that we'll eventually model physically to a phase where we're going beyond what's possible to be done in physical modeling?
Yeah, that's a really tough question. But I think when working with some new materials like knitted textile, crocheting, and these malleable materials that also have the have a multi-directional behavior, it's really hard to depend on the only computational tools without going through iterative processes of the physical model making. So I think although the computational tools are really developed too much, and some of them are really amazing, but we still need to do the physical modeling. Otherwise, we cannot trust the results of the computational tools. I couldn't trust, because I use some of these simulation tools that are kind of developed for the woven textiles that consider just two-directional behavior of the textile. So those are not, you cannot use them for simulating some materials like the knitted textile. So either new tools should be developed, or you should find a way to kind of tweak the tools that are already developed to kind of simulate these new material behaviors. So I chose the second path. Instead of developing new tools, I focus on how I can use the available tools to make it work for this particular material.
Thank you. I want to open it up to the whole panel. The other three authors have been deploying contemporary and advanced tools, including machine learning, and also, I think, blockchain structures as well. So these are the kind of digital tools that we've only been working with for the last few years. And perhaps a general point of discussion could be, are we presently in a new phase of the quote-unquote algorithmic project in architecture? If you're considering something happening at the end of the last century with computer-aided design and perhaps at the beginning of this one with parametrics, is this AI a fundamentally different phase that we're entering? Or to be more specific, is the relationship that we have with the machine more on an eye level or a genuine collaboration than it was only 5 or 10 years ago? Maybe this is a question for Matthias or for Daniel, both of you.
I take it, I'm always speculative. The relation fundamentally is different. When you look now to the development or the cry on social media, what happened with the diffusion models, and I say, hey, AI came to architecture. Now everyone with access, or with a cell phone, with access to the internet, can instantly design anything from everything, from everywhere. We never had that. It's an entire democratization of what means design, and it means also the whole project of digital is getting rid of experts, or the third party, or however you call it. That means we have, of course, drastically to reinvent what it means to design, or what we develop. And I don't think that we can keep pace with the development of tools. We don't have the resources anymore as architects. The knowledge is too specific. Computational or computer scientists projects, they're developed by teams of, maybe look at DeepMind, there's hundreds, thousands of people working on AlphaFold. We don't have the financial resources, which is, as I said before, the training of one of these supermodels takes supercomputers, takes 1 million more for only an instance to simulate. So, yeah.
Thank you. Matthias?
I mean, we're in a sort of more traditional AI realm in some way. So, I never really consider myself to be very involved with artificial intelligence, as it's just agent-based modeling. I mean, I really believe it's, especially for what we do, it's a great tool. I mean, it's very accessible and it's very immediate, and it's also it just allows to set up a system, especially in the context that ours is, where you can represent a system that kind of will eventually exist, like our adaptive structures, where it's kind of beyond the design tool, but more the brain that will become sort of what the non-material manifestation of that system. So in that sense, in our case, this is very applicable, but I don't think it's usually what would now be put in the box of all the things that Daniel mentioned.
Thank you, Matthias. Are there any questions in the audience? Over there, please.
I just have the question for maybe Matthias. You talk about the agents, they vote together to form the topology. Could you talk a little bit about how that was done?
I mean, so the agents have behaviors, right? So, that's what we define. So basically, that's our interface for designing. And these behaviors are just like intentions. They want to do something, and these intentions are informed by feedback. In our case now, what we have seen, these matrices. So basically, they have this feedback, and they're told to, you want, maybe to go to a certain value, or don't want to have connections with so many other agents. So what they then do is they vote. It's I have 5 elements, this one meh, this one I would like to add, and then sort of it communicates with its neighboring agents, and what do you think about them? And then okay, let's do it. And then this changes the whole game again. And then this goes and goes and goes and goes, iteration over iteration, until you find some sort of equilibrium where everyone is as happy as one can possibly be, or like or less satisfied. Let's put it that way. And that's why it's kind of scalable in a certain way, because you can like add behaviors, right? And they would be sort of like incorporated in this thing, and then you can give priorities to some, and that you can also understand how certain like intentions will unfold in a sort of like in the topology, for example. So I could also see like, what if each agent only has 4 connections, right? Then how would that sort of like translate to an adaptable topology and things like this? So it's kind of for modeling and for designing, but really also for exploring and understanding, just by sort of like tuning behaviors and describing them in different ways.
I just want to extend from your answer, Matthias, like in terms of like everyone is happy, like do you maximize the happiness or like minimize sadness in the agent-based modeling, you know, like what is better way of optimizing in that scenario?
I mean, that's kind of a philosophical question, right? If an equilibrium is like is the glass half full or half empty? I guess maximizing happiness sounds better than minimizing sadness. I mean, it also really depends, right? Because like there's so many objectives that will eventually be conflicting, right? It's naive that you could say like, wait, let's put 100 objectives into the bucket and then it's gonna like magically resolve everything. So our engineers, they're always like curious, like what does the perfect adaptive structure look like? But they like don't care if this would be functional at all, right? If it has like 5 million elements you can't even walk through, they're like, cool. So once we introduce this to an architectural application, it will not be the perfect adaptive structure, right? Because it also has to be functional. Would it be perfectly functional? Sometimes you maybe have to accept the diagonal, right? So it's a bit of it's just compromising. Is it worth it? It's kind of mediating between interests and stuff like this. So that's why we also don't conceive of this as an optimization problem, right? Because there's probably not one solution that is amazing, but many that are like different in good in different ways.
Thank you for the question about happiness. Maybe we can move from happiness of agents to the happiness of students and address one more topic tonight or this afternoon. Since we're here at Penn and next to research, we also do teaching. When I listened to Daniel's fantastic presentation, I got a sense that he's on a way to develop a new kind of typology, really. And if typology once was considered the teaching method and science of architecture, perhaps 200 years ago with Durand, do you see that your forward-looking new kind of typology would have an impact in the education of architects as well?
Yeah, what I've shown is is a lot of also my didactic model for how I work with students. And I mean, what we can bring in or like to any kind of, not only computation is always our history. And this is typological thinking. There's like, what is a building actually, how it relates to a city, how it relates to materials, whatever you can do, take. So somehow a building always centers or architecture around the notion of typology. And when we can, what means reinvent, or when we can have alternative versions of that, I think we can have, again, like a greater stance as experts in interdisciplinary teams, actually, not like contribute as architects. And this is like what I want to take on, also to take for students with how you can get more, being more participative in a discussion on city. And one takeaway for students, please design more buildings in future. It's always so less buildings what we talk when we relate to digital design as an application.
All right, thank you so much. And thank you everyone for wonderful presentations and questions. Enjoy the rest of the conference.